Hi everybody, welcome to our first lecture on the idea of waves, wave motion, something called simple harmonic motion, and along the way we're going to look at a couple different kinds of waves. To begin with, we're going to talk about mechanical waves, and later on we'll look at something called an electromagnetic wave. So to start with the idea of a mechanical wave, well, what is a wave? Well, in the end, whether mechanical or electromagnetic, all waves are simply energy in some form or another. But mechanical waves result from some sort of vibration, okay? And mechanical waves require a medium through which to travel. They require some sort of material to travel through. Okay, so there are different types of these waves. Earthquakes are examples of mechanical waves. They move through the medium of the earth. Wind can create waves. On most ocean waves are actually the result of wind blowing on the water. Sound is a mechanical wave, and it requires things like air or water or anything like that to travel through. For example, sound cannot travel through the vacuum of space because there is no medium to travel through. So that's one of the most important ideas behind a mechanical wave, is that it does require a medium through which to move. Okay? No medium, the mechanical wave can't go anywhere. The energy can't travel from one point to another. And again, the medium is simply whatever that material is you're traveling through. But what's interesting is the waves are sort of an energy in motion, a transport, as energy moves from one point to the other, but it actually doesn't take the medium with it. Now, what do I mean by that? Well, let's say there's a little toy boat floating in a pool, and your friend comes along and decides he's going to cannonball into the water. Okay. Now, of course, up here he has some sort of potential energy that eventually is going to result into kinetic energy. But when he slams into the water, that kinetic energy creates that initial wave, okay, that's going to form there. Okay. And we still got our little boat that's waiting for that wave. Now, when the wave reaches the boat, it causes that boat to bob up and down. But the boat doesn't go anywhere, so that after the wave has passed, the boat remains there. Now, that basically means that it didn't take the boat or the water anywhere with it. The water was just the medium through which the energy was transported along the way. The really big tsunami that happened a number of years ago, I think around 2003, there were many boats in the path of that tsunami who never knew it passed underneath them. They simply moved up and down with the water as the energy passed through. One of the ideas behind some types of wave motion is some wave motion can exhibit something called simple harmonic motion, which I've abbreviated as SHM. And something in simple harmonic motion has the ability to oscillate. That means to move back and forth regularly around an equilibrium point. Okay? Now, that's different from periodic motion. Periodic motion is something that's repeated over and over and over again with the same time frame. But that doesn't mean there's really an equilibrium point. For example, if you bounce a basketball at the exact same time it goes from your hand over and over and over again, that's a periodic motion. But there's no equilibrium point, because the equilibrium point is really the basketball sitting on the ground. It doesn't have the ability to go below the ground and come back up. Now, typically though, anything that exhibits simple harmonic motion has to have some sort of force that always is trying to return it to its equilibrium point. And that's a principle behind something called Hooke's law. Okay, and Hooke's law is a way of expressing this restoring force, particularly around the idea of a spring. Because it's really just a mathematical equation for a spring force. Spring force is equal to negative kx. Now that negative is interesting. This is one of those things in physics where the negative is a concept negative, not really a math negative. Okay? Because what it's saying is that the spring force is a reaction force, not an action force. In other words, if you have a spring can't act on its own. So if you pull on it with a force, the spring force will be automatically in the opposite direction. Okay? Equally, if you compress a spring, that spring is going to push back with that equal and opposite force. Okay. Now a reminder, K stands for the elastic constant, and X is the distance of how far you stretch it. Okay. So clearly what that means is the spring force is very related to how far you stretch something and how strong the spring actually is. So for example here, in this sort of simulation here, if we hang a mass on this spring, okay, notice it stretches a certain distance. Okay, but if I increase the strength of the spring, it no longer stretches as far, okay, due to the stronger spring. Okay. Equally, it takes more force now to stretch this than it does when it's a much easier to stretch spring. So if we look at an example of dealing with this in Hooke's law, I've got two separate springs here. Both of them I've attached a 500-gram mass to. Now in the first case, the spring stretched 20 centimeters, and in the second case, the other spring stretched only 10 centimeters. And the idea is to determine what is the elastic constant of each spring. Well, as you can see off to the right, I've clearly drawn a free body diagram, right? So what would the forces be? Well, obviously we have gravity pulling it down, and we're going to have this spring force supporting it. Now, if it's just sitting there at rest after we let it stretched, it must be in equilibrium. That means that that spring force and the weight are equal to each other. Now, in substituting, I'm going to put kx for the spring force. Notice I didn't put negative kx. Again, the negative is more of a concept negative than a calculated negative. And so k would be the weight, mg, over how far you stretch it. So the first k value, k1, would be the mass, 500 grams, which is 0.5 kilograms, times gravity, all divided by 0.2 meters, at 20 centimeters, which gives an elastic constant of 25 newtons per meter. For K2, well, you can probably already guess, if it's the same mass, but it only stretched half as far, that means it's stronger, okay? So what it means is that it's going to have a higher elastic constant, okay? Double the elastic constant because it only stretched half as far. And that's basically the idea behind Hooke's law for springs, okay, and how that's sort of related to this. Again, that negative there means that whatever spring force you have is going to simply impose some other force. Now, what that means, though, is when you have something that has the ability to oscillate around an equilibrium point, then it's going to exhibit this simple harmonic motion. What I mean by that, as we can see in the simulation, is that right now this is in equilibrium. Okay, it's sitting at rest. If I pull it back a little bit from equilibrium, it will now oscillate very regularly around that equilibrium point, back and forth, back and forth, back and forth. Okay. Now, one thing you'll notice is that the distance it's traveling up and the distance it's traveling down from this little dotted line, equilibrium, appears to be exactly the same and is very regular. Also, notice the time. Keeps taking about the same time to go back and forth every time. And that's what exhibits simple harmonic motion. The fact that this thing oscillates regularly around this equilibrium point over and over and over again. Anything that shows that type of motion has simple harmonic motion. Turns out there are three things that appear in the simple harmonic motion. By the way, these three things will also appear in the idea of basic wave motion. So all simple harmonic motion and all wave motion contain the following three things. First of all, the wave or the motion has a certain amplitude, symbolized by A. Amplitude is your maximum displacement from equilibrium. In other words, how far did you displace that thing from equilibrium? The second part is called the period, which is given by a capital T. Just like in planetary motion, the period, the time to go around the sun, for example, for the Earth, period is a time frame. And this is the case of where it is the time to execute what's called one complete cycle. In other words, the amount of time, in the case of that mass, to go up and down once. That's one cycle. And then the last part, frequency, given by a lowercase f, is the number of cycles per time period, which is given in the unit Hz, which stands for the hertz. Now, for example, if I was to graph that spring in motion, okay, well, I start off and it is displaced a certain distance from equilibrium. Okay, the horizontal center line there is equilibrium. It then heads towards equilibrium, comes a certain distance beyond that, and then returns. And it keeps repeating that motion. Now, if you think about it, in those three things, this distance here or this distance here is roughly the same. That's our amplitude. Okay? Now, but if we begin right here, the next time we're back at this point is over here. So from here to here, whatever time that takes, that must be your period. Okay? The time it takes. Now, frequency is a little bit different. Frequency is saying, well, how many of these waves occur per time period, or really per second is really what it is. So, for example, if 1 second occurred right here, okay, well, I've only gotten halfway through the wave. Okay, so if 1 second was right there, then I'd have a frequency of 0.5 hertz, because I only got through half of a cycle in 1 second. Okay. If 1 second was over here where I got through one whole wave, well, then the frequency would be 1 hertz, because I got through an entire cycle. So, for example, if you look at the picture below, of something that's exhibiting simple harmonic motion. Well, first of all, what's the amplitude? Well, that's pretty easy because it goes from 0.2 meters down to negative 0.2 meters. So the amplitude must be 0.2 meters. Not too bad, right? Now the period, let's look. It starts here. It takes 4 seconds to get through one of these cycles. And then another 4 seconds and I'm through the next. And another 4 seconds and I'm through the next. So every 4 seconds it repeats. That must be the period. Now the frequency, well, if we take a 1 second mark, notice we only got through 1/4 of a wavelength. Okay? So if we only got through 1/4 of a wave in that 1 second, the frequency would be 1/4 or 0.25 hertz. By the way, do you notice the relationship between period and frequency? It looks like that if I were to invert period, in other words, take 1/4 seconds, I would get 0.25, which means that frequency must be the inverse of period. Okay, a very important idea. So, as we saw there, a spring exhibits this simple harmonic motion. Now, there's some interesting things that go along with it. I want to look at what specifically affects the period of this spring's motion, okay, as this mass oscillates back and forth. Okay, so there's two particular things we could look at: the amount of mass that we put on it and how strong the elastic constant is of the spring. How's that going to affect its motion, in particular its period? Well, I got a stopwatch here. Okay, so right now we notice we've got 250 grams hanging on here. Okay. So if we let it go, we can see it took about 0.97 seconds, almost a full second for it to go up and down once. That's its period. Okay. Let's change the mass. Now I've reduced the mass. Okay, so I've taken the mass down. It's lower than 250 grams. Okay, we're going to pull it back about the same distance. If we let it go, we now see it takes about 0.63 seconds. So clearly, as the mass goes down, the period goes down. It gets shorter and shorter as the mass goes down. In this next case, I have made the spring stronger. I've increased the elastic constant. Now remember, last time was about 0.63 seconds. Now it's about 0.37 seconds. So clearly as the K value goes up, the period also goes down. Okay, so clearly mass and elastic constant affect your period. And that's shown in the equation for the period on a spring. Period on a spring is 2 pi times the square root of the mass over the K value. So as mass goes up, period goes up, takes longer, but as K value goes up, period will go down, it's shorter. And then as we just discovered before, the frequency is the inverse of the period. Let's look at an example. Here I have a 200-gram mass hanging on a spring that has an elastic constant of 25 newtons per meter. And I want to know the period and frequency of its motion. Okay, well, period on a spring is 2 pi times the square root of m over k. So 2 pi times the square root, 200 grams, 0.2 kilograms, over k, 25 newtons per meter. Which gives a period of 0.56 seconds. And then to get the frequency, well, all I got to do is take the inverse of that period, or 1 over 0.56, which gives me a frequency of 1.78 hertz. So it'll go through 1.78 cycles in 1 second. That's not too bad. My question below, though, this is where people have some trouble with the algebra. Let's say I have the same spring that now has a 2-second period. I want to know how much mass I have hanging on there. Now the funny part is the algebra that goes in this. So we start off with 2 pi, the square root of m over k, right? Now, if we were to plug in the numbers, we have a period of 2 pi. The mass is under the square root, as is the 25. So algebraically, I divide by 2 pi, and then I square both sides to get rid of the square root. And then I multiply through by 25. And that tells me I have a mass of 2.53 kilograms hanging on that spring. Okay? I've seen people mess that algebra up a lot, so you might want to practice that one. Another device that we studied this year that clearly exhibits simple harmonic motion is a pendulum. Now, one of the things that we discovered when we did a lot of stuff with conservation of energy with a pendulum is how much the mass didn't seem to really matter to a lot of its motion. However, that may not be true for a period, but we can see here. So what I've got here are two different pendulums. Okay. Right now they have equal mass, but they're on different length strings. Okay. What I'm going to do is I'm going to pull one back about 30 degrees. And here I've got a timer here that's going to time its period. Okay. So we're going to let it go. And here it measured a period of 2.86 seconds, okay, for that pendulum, 2.86 seconds. Now, the other one that has the same mass but is on a different string, I'll also pull back, okay, and we'll let that go. 2.49 seconds, 2.5 seconds. So the one on the shorter string had a shorter period, even though they had the exact same mass. Okay, so clearly that shorter string must be affecting the period, not the actual mass. Okay, and that turns out to be very important to begin with. For one, the mass doesn't matter, but the length of the string does matter. Now, does anything else matter? Well, turns out something else does. Again, if we look at this first one here, okay, that had a period of 2.88 seconds. But that's here on Earth. What if we go to the moon, where gravity is much less? Okay, so we're going to let it go on the moon. Much longer period with lower gravity. Okay, so the two things that appear to affect the motion of a pendulum are the length of the string and the gravity surrounding it. The mass has nothing to do with it. And we can see that in the equation. Okay? The period of a pendulum is 2 pi times the square root of the length of the pendulum over the acceleration of gravity. Again, mass is not relevant. So, for example, let's say I want to create a 4-second pendulum here on Earth. How long of a pendulum do I need? Well, period of a pendulum, 2 pi, square root of L over G. Now we're looking at that length. It's under that square root thing, so some algebra is going to be involved here. Period is 4. Gravity in the Earth is 10. Let's divide by 2 pi. Square both sides. And then multiply by 10. And that means I need a little more than a 4-meter long string, so a really long string, in order to create a pendulum that would last 4 seconds in terms of period on Earth. Okay, so that's the idea of an introduction to the idea of waves. All waves are simply energy, the product of some sort of vibration. Mechanical waves require a medium, a material, to travel from one point to another. Anything that exhibits something called simple harmonic motion will oscillate regularly around an equilibrium point and has something called an amplitude, the maximum displacement from equilibrium, period, time to complete one cycle, and a frequency, the number of cycles per second. Two things that exhibit simple harmonic motion, a spring and a pendulum. And as we've reviewed, the period of a spring is based on its mass and its elastic constant. Frequency is the inverse of period. Pendulum's period is based on the length of the pendulum and gravity, and its frequency is also the inverse of period. All right, we'll see you next time.